Welcome to the deep dive. Really excited about today's topic. We're tackling something really critical, but maybe sometimes overlooked. It's the problem of partial data rights in Delta Lake on Databricks.
Hmm.
Think about it like, you're copying a file and halfway through it just stops, but it looks like the file is there. That's kind of what happens here. Your data gets silently messed up. And that can lead to some really flawed decisions down the line. It's a tricky one. We're digging into some great material today, excerpts from Detecting Partial Data Rights in Delta Lake on databricks.pdfs. So our mission really is to unpack these methods, see how they work, and give you a clear roadmap for protecting your own data from this sneaky issue.
Absolutely. And it's so important because, data integrity isn't just a nice to have, it's foundational.
Hmm.
If you want reliable data systems you can actually trust, you need to nail this. Having layers of checks, that's not overkill, it's smart strategy.
Okay, so let's really unpack this. Before we jump into the fixes,
Yeah.
what exactly are we talking about with a partial right? Why is it such a big deal?
Yeah, good question. So a partial write happens when you intend to write, say, a whole batch of rows into your Delta table,
Hmm.
but something goes wrong. Maybe only some rows make it in. Or maybe none of them do. And this could be because of anything. Really, system crashes, network hiccups, maybe the data itself was malformed coming in. The real kicker is it might look like the data is there,
Yeah.
but it's incomplete. And that's where you get bad analytics, wrong reports,
Yeah.
potentially big problems.
Okay, so it's data that seems okay but is actually missing pieces. Got it. So how do we catch this? What's the first tool in our toolbox?
The first one is built right into Delta Lake. It's Describe History.
Ah, the audit trail.
Exactly. Describe History keeps a detailed log, like an immutable record, of every single operation on your table. Write, merge, delete, you name it. Now, for spotting partial writes, you look at the operation column, make sure it says write, and then the critical part is operation metrics.num output rows. Let's say you were trying to write 5 rows. You run your job, check the history, and it says num output rows.
Ah,
Ugh.
okay. Red flag right there.
Big red flag. That mismatch tells you something suspicious happened. And there's also an optional field, user metadata. You can stick a Jobit in there, which helps a ton when you need to track down which job had the issue.
Right, so it's like having this meticulous built-in accountant for your data, always checking the ledger and flagging weird discrepancies.
That's a great way to put it. It's your first stop for figuring out what happened after the fact.
But does it tell you why it happened? Or just that the numbers are off?
Good point. It mainly tells you what happened, the operation, the row counts, the time. It doesn't inherently diagnose the why. For that, you'd usually take that Jobit you hopefully logged and go check your application logs, maybe system logs, see if there was a network error or something else around that time. So yeah, it's excellent for spotting issues, but maybe not the complete solution on its own for prevention or automatic fixes.
Okay, that makes sense. It's a great starting point, but maybe you need more. What if you want something more tailored, maybe for a specific ETL pipeline?
Exactly. That's where you might build your own right audit logging system.
Custom safeguards. Okay. How does that work?
Well, you basically create your own logging mechanism. Whenever your code performs a write operation, you log key details about it. Things like unique runid, maybe generate one using IZID so every run is distinct. Then the table name you're writing to, the that's how many rows your code thought it was going to write. And crucially, the actual rows, how many rows actually got written after the operation finished. You'd also probably want to write success flag, just a simple Boolean, get expected match actual, and a timestamp. Log it at. You could, for example, just append all this info into a dedicated monitoring table, maybe monitoring.write audit log. And the payoff here is pretty big. Later on, you can just query that audit table, find failed writes, partial writes where the counts are off, and use that runid to trace it right back to the specific job run that caused it. I've definitely seen cases where this kind of log quickly highlighted like an intermittent network problem that was causing tiny data losses that were otherwise really hard to spot.
Ah, okay. So here's where it gets really interesting. This isn't just about spotting problems after they happen. You're actually building a kind of self-monitoring system right into your process, like your own data detective.
Precisely. You're building that detailed audit trail specific to your application's logic.
But when does that extra effort, building and maintaining this custom system really make sense? Is it for everyone?
That's the trade-off, yeah. It's most valuable for those really complex, really critical ETL pipelines, maybe where you have custom logic deciding what gets written or multiple teams hitting the same tables, or if your data sources are, let's say, a bit unreliable. The detailed visibility and the ability to trace every write attempt back, that becomes gold. Basically, it pays off when data quality errors are expensive, or when you need that super granular, centralized audit record that goes beyond just the Delta history.
Gotcha. Okay, so that covers batch or more controlled writes. What about the world of streaming data? Things are moving fast there. Integrity must be paramount.
Absolutely. For streaming, the go-to solution involves streaming with checkpoints. The magic here comes from combining Delta Lake's atomicity, meaning writes are all or nothing, with Spark-structured streaming's checkpointing. So if a microbatch fails mid-write,
Sure.
say the network drops while it's writing to Delta, that write simply does not commit. Nothing partial gets into the table.
Oh, okay. It just rolls back.
Effectively, yes. When the streaming job restarts, it picks up right from the last successful checkpoint and retries that failed microbatch. This guarantees that you don't end up with incomplete data in your final table. It's a really fundamental feature for reliable streaming. And it also helps with detecting bad files coming in. Imagine a malformed CSV lands in your input directory. The stream's parser will likely fail on that file. You can catch these errors using query listers in Spark and log them so you know something went wrong upstream. There's also a useful option here called max files per trigger. You can set it like option max files per trigger 1. This tells the stream to only process, say, one new file each time it triggers. It helps manage the load, prevents getting overwhelmed by a sudden burst of files, and indirectly helps maintain stability, which reduces the chances of failures that could lead to partial writes if not for the checkpointing.
So what this all means for streaming, it's like having an automatic undo button, right? Coupled with a vigilant gatekeeper at the door. Ensures integrity even if things wobble midstream.
Exactly. The data that lands is guaranteed to be complete for each committed batch.
But quick question on that, if a batch fails and has to retry, does that mean a slight delay before that data shows up, even if it's eventually correct?
Yes, that's a fair point. There can be a small delay in availability. The job has to reprocess that failed chunk from the last checkpoint. For most applications, though, that brief latency is a totally acceptable trade-off for getting guaranteed data consistency. You just need to be aware of it, especially in super low latency scenarios. But the core integrity promise is solid.
Okay, makes sense. Now, what if just counting rows isn't enough? What if we need to be absolutely sure that every single piece of data within the rows made it correctly, like byte for byte?
Now you're talking about the deepest level of validation. That's where the row-level hash check comes in. This is for when data integrity is absolutely critical.
A hash check. Okay, tell me more.
So the idea is, before you write your data frame to the Delta table, you add a new column to it. Let's call it row hash. You generate this hash value for each row. A common way is using MD5 on a string that concatenates all the column values for that row, maybe separated by a pipe or something, like MD5 concats, div.columns. So if a row has values 1 alice 30, you concatenate them into 1 alice 30, calculate the MD5 hash of that string, and store it in the row hash column. Each row gets its own unique fingerprint.
Okay, like a digital signature for each row.
Pretty much. Then comes the validation part. After you've written the data to Delta, you immediately write it back into a separate data frame. Let's call it df written. Now you compare the original data frame, df, with the one you just read back, df written, using an operation like df.acceptall, df written. This acceptall finds any rows that were in your original df, but are not present, or are somehow different, in df written. If the result of that comparison, let's call it discrepancy, if discrepancy.count is greater than 0, you know you have a problem. It's a clear signal of a partial write or some kind of data corruption during the write. Like, if Charlie was in your original data, but acceptall shows Charlie in the discrepancy result, you know that row got lost or changed.
Wow. Okay, this is like giving every single row its own unique ID badge and then doing a precise roll call after the data transfer. If any badge is missing or looks altered, you know something's fundamentally wrong. That's incredibly granular.
It really is. It provides a very high degree of certainty about the data's integrity.
But that sounds computationally intensive. Generating hashes for every row, then reading everything back and comparing. How often is that really practical?
You're right, it definitely has a performance cost. Generating hashes, especially for wide tables or huge data sets, takes CPU time. And reading the data back adds I/O overhead. So it's not something you'd necessarily do for every single table in your lakehouse. It's best reserved for your absolute most critical data sets.
Like financial data or compliance stuff.
Exactly.
Yeah.
Financial transactions, maybe sensitive PII or medical records, regulatory reporting data, anywhere that even one missing or altered row could have serious consequences. It's a powerful tool, but you use it strategically, where the cost is justified by the need for near-perfect integrity.
Okay, that makes perfect sense. It's a heavyweight tool for heavyweight data. Now, sometimes the simplest approach is best. What about just counting the rows?
Yep, row count validation. Simple, direct, and often very effective. Works for both batch and streaming too.
How's it work? Just count before and after?
Pretty much. After your write operation finishes, you get the actual count of rows that ended up in the delta table. You compare that to the expected count you had before the write started. If actual count isn't equal to expected count, boom, you know something went wrong. You can raise an exception right there, maybe log a clear error message like, partial write detected, expected 1,000, got 990.
Nice and clear.
Yeah. The key tip here, though, is don't hard code that expected count in your check.
Right, because the source data might change.
Exactly. Instead, get the count from your source data frame right before you write it, like df.count. Or, if you need to track it across steps, maybe store that expected count in that audit log we talked about earlier, or some other metadata store. Keep it dynamic.
Makes sense. So this is the direct approach, quick count, immediate feedback if things don't line up, no deep forensics needed right away.
Correct. It catches the most common type of partial write missing rows very efficiently.
Okay, so we've talked a lot about detecting issues after they happen or ensuring writes are atomic. But can we be more proactive? Can we stop bad or incomplete data from even getting partially written in the first place?
Yes, absolutely. And that brings us to delta constraints. These work a bit differently. They help indirectly by enforcing data quality at the point of write.
Constraints, like database constraints.
Pretty much. You define rules directly on the delta table using SQL commands. For instance, you could add a check constraint like alter table, mutable add constraint, id not null check. Id is not a null.
So enforcing that the odd column can never be null.
Right. Now, if you try to write data and one of the rows has id set to none or null, that entire write operation will fail.
The whole write fails, not just that one row.
The whole transaction attempting the write fails. Delta Lake ensures atomicity here too. It won't let the invalid row in, and therefore the write operation itself is blocked. You'll get an error, an analysis exception, telling you exactly which constraint was violated and by which row values. So these constraints act like guardrails. They stop bad data like nulls where they shouldn't be, or maybe values outside an expected range from ever entering the table. By ensuring only valid data gets written, they uphold the quality of whatever does successfully land in the table. It's a powerful, proactive defense mechanism.
Okay, this raises an important distinction then. While this method might not catch a situation where, say, half the valid rows didn't make it due to a network drop,
Correct.
it absolutely stops a partial write that includes invalid data according to your rules. And preventing bad data is just as critical for overall integrity. It's a proactive shield for data quality.
Precisely. It ensures the data that is written meets your defined standards.
Interesting. Okay, so we have built-in history, custom logs, streaming guarantees, deep hashing, simple counts, proactive constraints. What about a more modern, perhaps integrated approach for managing quality across an entire pipeline?
That leads us nicely into Delta Live Tables, or DLT, specifically its expectations feature. This is a more declarative way to manage data quality throughout your pipelines.
DLT expectations, how does that work?
So within a DLT pipeline, typically defined in Python or SQL, you declare your data transformations using decorators, like at dlt.table, and right alongside your transformation logic, you can add at dlt.expectRules. For example, at dlt.expectValided, ed I not null. You give the rule a name, validate, and define the condition ed as not null. DLT takes over from there. It automatically tracks how many records pass or fail this expectation during the pipeline run. It logs all this information and enforces the rule.
Enforces how? Does it stop the pipeline?
It gives you options. By default, if a record fails an expectation, DLT will typically drock that record. So only data meeting your quality criteria flows through to the target table. But you can also configure it to keep the bad records, but flag them, or even automatically route them to a separate quarantine table for later analysis. Plus, DLT provides built-in observability dashboards. You get a clear view of data quality metrics, how many records failed, which expectation, error logs, row counts, all automatically tracked and surfaced for you.
Okay, if we connect this to the bigger picture, DLT sounds like it builds quality control right into the pipeline's DNA. It's not a separate step. It's part of the definition.
Exactly. It's declarative QA.
So it automatically ensures only good, valid data progresses and gives you this really powerful built-in visibility if anything goes wrong with quality. That sounds incredibly useful for complex flows.
It really is. It shifts quality from something you bolt on afterwards to something that's integral to the pipeline itself.
Wow. Okay. We've covered a lot of ground here. Let's recap quickly. We started with the basics. Describe history, the built-in audit log.
Yep, the forensic tool.
Then custom write audit logging for tailored tracking.
More proactive, application-specific logging.
Streaming with checkpoints for that guaranteed atomicity in real-time flows.
Essential for streaming integrity.
The super deep row-level hash check for absolute row-by-row certainty on critical data.
The ultimate validation when needed.
Simple but effective row count validation.
Quick and easy check for missing rows.
Proactive delta constraints to block bad data at the gate.
Guardrails for data quality.
And finally, the integrated approach with DLT expectations for pipeline-wide declarative quality assurance.
Building quality in from the start.
That's 7 really distinct, powerful methods. Each seems to offer a unique layer of defense against this quiet threat of partial data rights.
And what's really key, I think, is that while each one is valuable on its own, the strongest strategies often involve layering these. You might use describe history for general monitoring, add row count validation to most jobs, maybe use delta constraints for critical columns, and deploy row-level hashes or DLT expectations for your most sensitive pipelines. It's about building that resilient, multi-layered system that automatically protects your data, which is, let's face it, probably your most valuable asset.
That's a fantastic point. It's not about picking just one, but combining them intelligently. Okay, final thought for everyone listening. As you think about your own data pipelines, the ones processing that crucial data, maybe ask yourself, which of these methods we talked about today could give you the biggest immediate win, the quickest boost to your peace of mind about data quality? And then maybe, what's the next logical step you could take? What's the next layer you could add to build an even stronger, more impenetrable fortress around your data's integrity? Something to mull over.